These are the audio notes for Chem 1 dealing with solutions. We're going to go over some of the vocabulary that you need to be aware of and give you a little introduction to what you're going to be seeing in the laboratory next class period. Now, my first slide, I'd actually prefer to switch over to Smart Notebook for. So instead of writing it down as I'm showing right now, why don't you instead write it down how I'm about to show you. In chemistry, we talk about matter. We've talked about the conservation of matter. Well, there's two types of matter. There are pure substances, which we talked about last semester, elements and compounds. And there are mixtures. Now, I apologize that this is all kind of bunched together. So what I'm going to do is kind of separate this out. So we are focused on everything to the left of that green line. Now, a mixture means it's not the same throughout, that its properties can change based upon how you make it. There's only one way to make H2O water. There's only one way to make copper metal. So that's why pure substances are different than mixtures. Now, in this flow chart, there's two types of mixtures, homogeneous and heterogeneous. Homogeneous things look the same throughout. For example, alloys. We talked about alloys last semester when we talked about metallic bonding. Now, on my previous slide, amalgam is a specific type of alloy that has mercury, not something, a vocabulary term that you need to be aware of. Solutions. We will talk more about solutions specifically on my next slide. However, solutions is kind of the liquid version of a homogeneous mixture where it looks the same throughout. Up on my front lab bench, there is a soda called Dew Shine, a Mountain Dew version without the yellow food coloring in it. If you look at the back label, there are several ingredients. That's how you know it's a mixture. It's not just one thing, but it looks the same throughout. Heterogeneous mixtures do not look the same throughout. Also on my lab bench is a jar filled with a mixture of oil and water. The oil is on top of the water because oil is less dense than water. If my sub would like to shake up that jar a little bit, you'll notice that they might be able to mix a little bit for a second, but eventually they come back to two separate layers. And to be heterogeneous means it's not the same throughout. You can see the different parts. A suspension is going to be when you have a solid mixed with water or any other liquid, I suppose, but it's not able to stay mixed. So what happens is the solid will usually settle to the bottom. An example I like to give of that is if you've ever gone to a place that has a beach cabin, they might have a pail of water outside the cabin for you to rinse off your feet before walking in to get all the sand off. That sand all ends up at the bottom of the bucket. It does not actually mix with the water. Finally, a heterogeneous type of mixture that we will not be showing you much in the lab because it's a little more unusual is a colloid. I actually have a soda called an Orbitz. I think it's from the early 2000s or late 1990s, where little pieces of gum are floating within the soda itself. That's also on the front lab bench. That's where the solid is floating, not settling to the bottom, but you can still see distinct layers. So again, here are those terms. Feel free again to pause the video if any point comes along. But this half of our physical change unit is now going to focus on solutions. So I'd like to start off with the definition from the textbook of a solution. It's a mixture of two or more substances uniformly dispersed throughout a single phase. Again, take a moment to jot that down. However, this is the problem with a textbook definition instead of putting it in your own words. What in the world does that statement mean? Well, first off, let's break it apart. Uniformly dispersed means it's spread out evenly. You don't have one area where all of the substance is and the other area where there isn't much stuff. It's all spread out evenly. A single phase. In a solution's case, it's all liquid. In an alloy's case, it'd be all solid. You can't tell the different metals mixed to make a trumpet. It's all the same throughout. Well, when you look at that soda in the front of the classroom, you can't tell all the different substances that are in it. It's all the same phase. It's all liquid. So again, we are focusing on solutions for the majority of this unit now that we've gone past phase change. My last slide for today is, in order to discuss solutions, we have to have common vocabulary. So here is my first two terms that we need to know: solvent and solute. Solvent is kind of the thing that's doing the dissolving. Water is a great solvent. Water is actually referred to as the universal solvent. Solute is the thing being dissolved. For example, if we had a saltwater solution, we had salt to water and mix, the salt is the thing being dissolved. We'll show you in a little bit how that mechanism actually occurs. So salt being dissolved in the water. Last two terms. Miscible is just a fancy word for being able to be mixed. Which another term we can use for that is called soluble. If something is water soluble, it mixes with water. For example, you probably earlier in the class had vis-a-vis or washable markers getting soaked up by water on a coffee filter. Vis-a-vis or washable markers are water soluble. They're able to mix with the water. Immiscible means it's not able to mix, or it's called insoluble. Permanent markers are insoluble in water. They do not mix with water, as you saw with the coffee filter paper chromatography activity. However, you did see the permanent marker mix a little bit with the rubbing alcohol. And what we have to go over today and next class period is why some things are able to mix with other things. So why some things are miscible, why sometimes things are immiscible with one another. So that is really our goal coming here. In order to help us with that, we needed to be aware of this vocabulary set. This is all that we have for notes in our notebook. What I want to do now is transition into this sheet that you picked up on the way in. So feel free to pause the video while students get this out, and then we're going to work on this sheet together. Very top of the sheet, like dissolves like. This is our general phrase when dealing with why some things are able to mix with other things. However, we have to be careful with dealing with like dissolves like. If you read the second sentence, it says things with charges, which are either ionic things that have full charges, or polar covalent, which has partial charges, to mix with other things because charges can attract to one another. Prior to this note sheet, I had you trying to fill in a sheet that was titled Solution Notes Introduction to Water. And one of the things that we wanted you to try to figure out was how are things able to mix. The second sentence really describes why that occurs. Things without charges, non-polar covalent, can only mix with other things without charges. Again, solute and solvent are brought up in the second paragraph. I want to show you a skill that you need to know in Chem 1 of how to draw dissolving. I've divided this into 3 parts for this worksheet. So part 1 says draw the Lewis dot structure for the compounds listed, indicate charges. Well, it's asking for water and lithium fluoride as my 2 substances. So again, going back to that solution note sheet, hopefully you remember that water is polar covalent with a partial negative end near the oxygen, because oxygen has a greater electronegativity than hydrogen, so there's an unequal sharing of electrons, and a partial positive end near the hydrogen. Notice how I drew water kind of in this bent configuration instead of in a straight line across. This is how we want you to draw water. Lithium fluoride is an ionic compound. It is composed of lithium ions, that's a +1 charge, and fluoride ions with a -1 charge. And we could add our 8 electrons to show that fluoride is at the octet. Please keep in mind, however, that you could have things that are a +2 or a -2. Hopefully you remember why that is the way that it is. Okay, if we move down to the next part, which I'm going to have to erase this before I scroll down. It says redraw the Lewis structure so that opposite charges are next to each other. Remember, opposite charges attract. So if I draw my lithium fluoride, lithium is a plus charge. The part of water that's going to be next to the lithium fluoride is the oxygen end. The reason that is the oxygen end is the partial negative end. A polar covalent molecule with partial charges can attract an ionic compound with full charges. My fluoride, my F-, it'd be the hydrogen end of water. That would be next to that because the hydrogen end is the partial positive end. One of the things that we're going to look for when you are drawing dissolving is, do opposite charges match up? So as you can see, when water dissolves an ionic compound like lithium fluoride, the positive end of the lithium is attracted to the partial negative end of the water. Finally, in order for dissolving to occur, there must be multiple solvent molecules. As I state in this number 3, solvent surrounds the solute. Next, if it's ionic, the ions get separated. So LiF no longer sticks together. It's pulled apart. So the first thing I'm going to draw, and I'm going to do this in a couple different colors to help out. Lithium ion gets separated from fluoride ion. Now waters surround. Hopefully you make sure that the opposite partial charges attract. Typically, in the dissolving process, it is multiple waters around each part. I would say a minimum of like 5 or 6. We usually accept as long as you put 3 solvents around. You notice how my oxygen end is around the lithium ion? This would be drawing the dissolving of lithium fluoride. Now, I do not have other examples on the back side of this sheet, but what I'd like you to do right now is flip to the back side, and I'll just go over 2 more examples with you, because this is an example of an ionic compound dissolved in water. Well, how about a polar covalent compound dissolved in water? So what if we have hydrogen fluoride in water? First thing to recognize is HF is not ionic. It's not a metal and a nonmetal. It's not a cation and an anion. Instead, it's a covalent compound. I picked HF because most people can recognize it is polar covalent, where the fluorine has a partial negative end due to it being the most electronegative element, a greater pulling or sharing of the electrons. The hydrogen being the partial positive end. Unlike in the drawing of the ionic dissolved in water, when you dissolve a polar covalent in water, it does not split apart. You cannot break a covalent bond.
that HF bond. Similar to how the ionic dissolves in water, opposite charges do match up. So for water, the hydrogen end is the partial positive end. It's attracted to the partial negative fluorine end. And again, if it helps, I can draw the partial positives in. The oxygen then is attracted to the hydrogen. And again, show multiple, at least 3 waters surrounding. So the difference between an ionic dissolving and a polar covalent dissolving, the difference being the ionic breaks apart. The polar covalent does not. Similarities, they both get surrounded, and opposite charges match up. Lastly, what happens if we try to put hydrogen in water? Once again, hydrogen, nonmetals, is a covalent compound. So you immediately know that there will not be any splitting apart of the hydrogens. This is something that you do need to keep track of. However, hydrogen is a non-polar covalent molecule, meaning it does not have a partial positive and a partial negative end, meaning it cannot be attracted to water. It will not mix in water. So this does not mix. That doesn't mean we can't draw it still. What will happen is water will still be able to hydrogen bond. Remember that connection between 2 waters? You'll still be able to hydrogen bond with itself, attract to itself. You're going to end up with 2 layers, a layer of hydrogen and a layer of water. Similar to, on my front lab bench, a layer of oil and a layer of water. On your homework for tonight, and sooner than that, the activity you're about to work on, you are going to have to draw out sometimes things mixing and sometimes things not mixing. And hopefully the last 3 drawings that I've drawn will help you out with that, because that is the goal for the next activity, that is the goal for the homework, and quite frankly, the lab that you'll be doing next class period all will have this skill of drawing dissolving, or in this last case, not dissolving, that you'll have to be able to demonstrate. This wraps up not only the notes on solutions, but then the worksheet on drawing dissolving.